Okay, so sorry about that. Hoping it will be better now for the sound. So just to go back quickly over what I already said, so I'll just go quickly, but remember there's about 20 to 30 seconds delay between the moment I talk to you and the moment you hear what I say. So if there's a small delay when you ask questions, just remember that it is normal. You can post your questions in the chat, in the chat feature of YouTube. Just remember also that you need to be connected to a Google account to do that. Just taking my note, making sure I don't forget anything. That seems to be about it. Just quickly, my name is Anne-Marie. I'm product manager for the Surface product line. So Surface product line at Eddyfi is mainly working with eddy current array. So we have different product line, but on our side, we mainly deal with solutions to inspect surface of conductive material using eddy currents array. We are addressing different applications or challenges, so it can be cracks, corrosion, pittings, even in some cases finding material properties variation within the material. We're talking about eddy currents, so once again, as most of you probably know, or maybe you don't, but we are limited to the first few millimeters of the component under inspection. So that are the big lines about eddy current array. So if you are not someone who's working a lot with that, that gives you a bit of an idea of what we're doing on our team. I've been with Eddyfi for a little bit more than 10 years now, been involved with ECA all that time, so I should be able to answer all of your questions at the end of the presentation. Okay, so let's start with why we are actually here today. As I mentioned earlier, we will soon be launching Magnifi 4.7 in a week or two approximately, if I remember correctly. So we wanted to take this opportunity to present the features so you can think about it a little bit and want to upgrade when we will launch the release shortly. So the first feature is what we call the Liftoff Assistant. So when we're doing a current inspection, if we want to get good results, we need to adjust the signal at the beginning of an inspection. So whether it is really at the beginning or along the inspection, you might need to adjust the signal rotation a little bit. So this will be needed if you're changing frequency. So if you remain on the same material but you want to try a different frequency, you will need to rotate the signal. Or if you're doing a job, there are hundreds of pipes. When you're going from one to the other, there might be some small variations that will affect the signal rotation, so you might want to adjust it rapidly. So that's the idea behind this tool, making it easier to do that rotation. So most commonly, and that's the example I will be using today, but most commonly what we want to do is to rotate the liftoff to the horizontal. This is quite a universal reference signal that we can use to perform the rotation, so that's why I'll be using that as an example today. What we see on the screen right now, so here what we see on the screen, you have at the top, first C-scan, so and on the right side, I think now you see the cursor. So on the right side, you have the Impedence Plan. So this is at a specific frequency on a specific material. So let's say we are working at 500 kilohertz on stainless steel. We haven't performed any rotation. We get the upper image. So as you can see, the liftoff is at the vertical, the defect signal is randomly displayed. So the C-scan image is not the best to perform the analysis. On the bottom part of the image, it's the same scan, so the same data file, but we rotated the signal. So what we see is the liftoff flat section is on the horizontal axis, and the defect now has a really nice vertical components. And it translates in the C-scan as anything that is below 0 in the blue range of color, and what is above, indications or cracks or pittings, are orange and red. So that's one of the reasons we want to rotate the signal, just to make sure that what we see on the screen is what actually interests us. So it doesn't change the response or the sensitivity, but it's really a question of display and making sure that when we do the analysis, we are looking at something that actually talks to us. When we are working with array probes, it is highly recommended to use an encoder. So because in many probes there are 2 rows of coils, and we just want to make sure that everything is aligned. And we also often use filters. Those 2 items are sometimes, I won't say problematic, but they make the signal rotation a little bit more complex, because if we just look at the encoder, if you want to get a data file to rotate your liftoff signal, what you need to do is you have your material, your probe, you balance on the material, and then you lift the probe, and then you put it back. If you lift the probe, that means that the encoder is not moving on the surface, so you won't get any data point. That means that in order to get your liftoff signal, you will need to be based on clock instead of on encoder. If I go to the next image, so that's one limitation coming from the encoder, but I was also talking about the filter. So on the top C-scan here, we have a raw data with no filters, and at the bottom, what we see is the exact same data file, but with a median filter applied. So we don't see the liftoff signal anymore. So if we wanted to do the rotation with the filters activated, we basically would not be able to do a good job. That means that in order to be able to do your signal rotation, you need to deactivate the encoder and the filters. With the current state of things, so with how it's made right now in most of the software, you need to go deactivate those encoders and filters manually. So that's a couple of different windows that you need to access, do the rotation, and then go back and reactivate everything. So it's multiple manual steps, and there are risks to forget something along the way. So it's not a big issue if you forget to reactivate your filter. You'll clearly see it in your data file in many applications, and then you just need to go back after and reactivate it and redo your scan. But that's a little bit annoying when you're on a job and you want to get things done, and you want to get things done correctly. So it can be annoying. So that's why we wanted to change that, make it more easy to use and less operator dependent. So if I summarize quickly what I just mentioned in different aspects. So the Liftoff Assistant is a software assistant to facilitate, on the slide it's written the liftoff signal, but you could use any reference signal. You could rotate based on a signal coming from a notch, or you could rotate on the background noise. So if you have an application where the liftoff is very well controlled, but the material has some property changes inducing noise, you could also use that reference. So it's called the Liftoff Assistant, but it's basically a tool to help rotate the signal. We worked on that in order to help you save time during the probe calibration process. What it does, when you enter the mode, the software will automatically disable the encoder, disable the C-scan filters. It will display the liftoff signal or the entire signal of a group of channels simultaneously in the impedance plan. So that's what we call the render cursor. When I'll do the demonstration, I'll cover that in more details. The software will also do a best fit and adjust the cursor size to grab the data of interest. And once you're satisfied with your rotation, when you exit the mode, the encoder and filters will automatically be re-enabled. So you saved time if you used the Liftoff Assistant tool. I will move in Magnifi here. So I'll do a quick demonstration. So apologies, some of the steps will not be exactly as what you will see when using the equipment, because I will be using a pre-recorded data file because I don't have the equipment with me at home today, but it will give you the main steps to use the Liftoff Assistant. So normally when you will be working, you will be in the front stage. Most likely you'll start in the home menu. So if you want to do your signal rotation, the first thing to do is to access the calibration ribbon. So you find the ribbon at the top of Magnifi, and the Liftoff Assistant is the first button on the left. When you click on the Liftoff Assistant, you will have a small window that will pop up on your screen. There are no actions to take in that window, but it's basically just a reminder to help you remember what you have to do. So you can collapse or open the instruction, and it's really just a couple of bullet points to help you go through all the different steps. If you close that window, you will be exiting the mode. So while you're doing your rotation, you will have to keep this small window open. I was talking about the render cursor display. So that's what you can see on the right side of the screen right now. So in the impedance plan, you can see multiple different lines. So I don't know exactly if it shows well on your screen at home, but there's one line that is darker than the others. It's the line where the cursor is placed in the C-scan, and all the other lines are the channels comprised between the top and bottom limit of the cursor. So that means, for example, in that case, the data was acquired with a probe with 32 actual channels. Right now in the impedance plan, I'm seeing approximately 16 different channels. So when I want to do the rotation, I can average everything out. One other thing you will notice also is the top and bottom bar of the impedance plan are black. So usually they are white as the rest of the layout, but in that case they are black, just to remind you that you are in the Liftoff Assistant mode, so that your encoders are disabled and your filter as well. Once you are ready to proceed, so right now there's already a data on the screen, but if you just arrived on site and you want to set up everything, the C-scan would be black and the impedance plan would be empty. The first thing to do is to null the probe. So if you are using small sample of the same material than the component under inspection, you will place the probe on that sample, balance the probe. Once this is done, you start an acquisition. So on the data file on the screen now, the big So I'll just to give you a better idea if I do that. Okay, so what you see on the screen right now is a real-time read back of the data we were seeing previously. So the red portion is the liftoff signal, and we see on the right here a notch signal. So when you're doing the liftoff rotation, you don't have to scan a notch. In that case, we did, but it's not essential. So the cursors, once again, I was reading back at data, so the software did not automatically place the cursor, but this is the actual display of the cursor you would be getting when using the tool. So if I go back in the tool, I have the render cursor display in the impedance plan. I see that the liftoff signal is not on the horizontal, so you need to use the rotation button at the top of the impedance plan, and then you can rotate the signal to the position you want. This data file is quite good. Most of the channels are very similar, but in some cases there could be more variations in between all the different channels. So the render cursor is where this will be really helpful. So you can make sure that it's the rotation is good for all the different channels. I will do the same for the transverse C-scan at the bottom. So we can see here there's much more variation on the transverse. So the channel where the cursor is placed is pretty much on the horizontal axis, but we can see that some other channels are still going up a little bit. So I could decide to lower everything more, and it could be an average for all the different channels. So once this is done, once you're satisfied with your signal rotation, you can exit the mode and then start your acquisition. I rotated the axial and transversal C-scan separately. If you are working with multiple frequencies, for example, in that case, if I was working with 2 different frequencies, I would have to rotate 4 different signal in 4 different impedance plan. I'll just have a quick look here. Sorry. Okay. And as I mentioned, when I exit the Liftoff Assistant tool, you can see that the impedance plan, the top and bottom bar return to the normal color. Okay. If I come back here, sorry, we are suddenly becoming video producers. We're not used to that, so apologies if I look like I'm searching for myself a little bit. Okay, so here, the second feature we worked on is what we call the calibration check. So we developed this one also with the same minding we had for the Liftoff Assistant tool. So once again, the idea is just to make it easier and less operator dependent. So for those of you who are familiar with eddy current, you know that it's always preferable, when possible, to perform a calibration of your probes before you start an inspection. In some cases, it's not possible or practical if we can't get a representative sample. But it's always good to at least verify that the entire array of the probe is pretty uniform and that all channels are alive. So that's another function that the CalCheck can achieve. Okay, so what we see on the screen right now are two array probes that we have. So the one on the bottom left is the spine probe. So this probe was launched last spring and it has 128 channels. The one on the upper right corner is the iFlex probe. This one has a smaller coverage, 64 channel with one topology, but you can activate more than one topology at the time. So once again, you can have up to 128 channel. If you are working at multiple frequencies, two frequencies, that means 256 channel per probe to manually validate when you are checking your calibration or when you are checking that your probe is functional. So that can be it takes time and there are risks. You can scroll through all the different channels and at some point you're just going too fast and you let one dead channel slip and then you're screwed for your inspection. So that's why we thought that the CalCheck feature would be very interesting, because we're coming with bigger probes, more channels to have larger coverage or more sensitivity. So that's the way things are going. So might as well make it easy to use. So I mentioned that ideally you would perform a calibration using a reference sample. So that's what we see on the left. We have a calibration plate with a reference notch. We scan it in the transverse direction and then the axial direction. That's great when you have a smaller probe. What we see on the right of this slide is the spine probe. The spine probe has a coverage of 8 inches. So if you want to have a sample for that, it means a really big sample and a very long notch. So it's expensive to get and it's not always fun to travel with that in the field under the rain. So we developed a small tool. It's an aluminum reference that you just need to move across the array. It provides a signal and we can do a functionality and uniformity check with that. So the CalCheck will work for both type of reference signal. And I'm showing that on the screen, but it could be something else depending on the situation in the application. I won't explain in details why, because I already did for the Liftoff Assistant tool. But once again, if you want to get a good signal for your CalCheck, you will need to deactivate the encoders and filters. So the CalCheck is partly similar to the Liftoff Assistant tool and to what it deactivates the encoder and filters and re-enable it when you exit the mode. So once again, a couple of steps that you won't have to manually do anymore. So to summarize, the CalCheck is an acquisition mode dedicated to probe functional test or calibration test. So if you don't have a reference sample, you can just make sure that all the sensors are alive and fairly uniform. If you were able to perform a calibration and you just want to make sure that it was correctly applied, then you also have the capability to do it. It was meant to lower the operator dependency. So it's sort of a go, no go. The software will look at the amplitude and phase value and make sure that they fit within the range that you defined in the menus. When you enter the calibration mode, the encoder is automatically disabled, filter as well. When you click on the check button that we'll see later, the software will automatically check the amplitude and phase value and make sure that they are as required. And when you exit the mode, the encoder and filters will be re-enabled. So once again, if I move in Magnifi, we are still looking at a feature that has been placed in the calibration ribbon. This time it's the second one on the left, so the Cal Check function. So, okay, it's not showing on the screen. Give me just a second. Great. Okay, so that is the window you will get when you enter the calibration check mode. I'll move it just a little bit. Okay. Once again, you have a set of instruction. You don't see my cursor. Okay. So once again, you have a set of instruction here that you can collapse if you don't need them, but they are always there if at some point you forget what's the next step. In the list here, you will have the different C-scan. You have the menu to edit your settings, so the tolerance you want to consider for your application. Same as the Liftoff Assistant, you will see that the top and bottom bar of the Impedence Plan are black. So once again, to remind you that you are in a special mode where your encoders and filters are deactivated. You balance the probe, you scan your reference. So if you are working with a spine probe, for example, you will balance the probe in the air, start an acquisition, move the small aluminum reference across the array and stop the acquisition. If you are using a reference plate, you will balance on your plate, start the acquisition, scan in the transverse direction, then rotate 90 degrees, scan for the actual signal, and then stop your acquisition. So if I come here, I will get you a data file on the screen. Oops. So what we see on the screen right now, we have a first signal on the left. So that's when we scanned our notch in the actual direction. And the signal we have on the right was obtained when we scanned in the transverse direction. So if I go back in the Cal Check mode, oh, the window disappeared again. Sorry. There we go. We see that we have only two C-scans. So in this setup file, I only have one frequency and I have the actual and transversal C-scan. I don't know if you noticed also, but when I entered the mode, the background signal changed a little bit. That's because the filters were deactivated. So if I exit the mode, the filter is now reapplied and I see that the background noise is pretty neat. When I enter the mode, it changes. That's normal, and that's something we want because the filter could affect the signal a little bit since we are not encoded. So that's a normal behavior in the software. So if I click, oh, you lost the window again. I'm really sorry about that. Okay, so I clicked on the edit settings at the bottom of the calibration check window. So this is where you will configure the parameters you want for your specific application. You have to configure everything for each C-scan individually, so the actual signal can have a different tolerance than the transverse, or you might want for a specific application only look at the actual channels, for example. You can control the amplitude or the phase or both if you want to. So for today, I'll just look at the signal amplitude. The type, you have automatic and manual. So if you select automatic, the software will calculate the average signal amplitude on all of the different channels, and that will be the reference, and then you can set a tolerance. So for example, I want all the channels to have the same amplitude plus or minus 0.25, for example. So I will enter 0.25 volts here. You can change the measurement mode if you want. When you use the manual type, it is you who decide what is the target value you want to achieve. So automatic mode will be useful when you're doing a functionality check. For example, when you're working with the spine probe, or if you just have a screwdriver to verify if your probe is working. While the manual type will be what you'll use if you want to check an actual calibration. So if you scanned the notch, calibrated your probe to have 5 volts on this specific notch, then your target value here will be 5 volts. And once again, I could keep the tolerance of plus or minus 0.25. That means that when I'll do the cal check, I want all channel to lie between 4.75 and 5.25 volts on a specific reference signal. So if I close this window, I'll go here. So I edited the settings. Now I'll place the cursor on, sorry, I'll move that here. I'll place the cursor on the reference I want to check. So in that case, I only configured settings for the actual indication. So I'll place the cursor on the actual indication, making sure that the cursor on the scan axis includes the entire signal. After that, in the cal check window, I will check the actual C-scan, and I will click on the check button at the bottom of the window here. As you can see, there's an orange X that appeared here, which means that the check failed. This is normal. This is the raw signal. I didn't perform the calibration yet. So the raw signal, it doesn't have the proper rotation, and it's around 2 or 3 volts in amplitude. So sorry, you don't see here. If I move here, so at the bottom of the impedance plan, you can see that on this specific channel we have 2.92 volts. This is not what I wanted to achieve. So for now, I'll perform the standard calibration. So once again, I'm sorry, there are a couple of steps that you will not be seeing on the screen. I apologize for that, but it's a standard calibration. So from the system button right here, I'm just going to do a standard calibration of the signal. I'm going to deactivate a couple of filters. I'll readjust the color palette. Oh, that's when you are online that it doesn't work. I'll just take a couple of seconds to go back to normal. Trying to juggle with, as I said, being suddenly a producer and engineer. So if you are indulgent with me for just a few seconds. Okay, there we go. Don't know what I did the first time, but clearly not the good thing. Okay, so I now calibrated the notch. So you see that the color in the C-scan changed. It's more red than it was. If you also look in the impedance plan, the phase changed. So we rotated the signal to have the liftoff at the horizontal. So if I go back in the cal check, where I set the tool to make sure that all channels lies between 4.75 and 5.25 volts, I will activate the actual check, and you here, and when I click on the check button, I still have a small difference, and I don't know why. So the calibration is not correctly applied. Just give me a sec, and I'll redo it. So I apologize for that. Okay. So I just adjusted the setting a little bit. I performed the check once again, and you can see now that I have a green check on the C-scan I just validated. So you place the cursor correctly on the indication, and then you perform the check here. And instead of scrolling manually through all of the 64 channel of the array probe and making sure that the amplitude value is correct, the software does it for yourself. I had some problem with my calibration here. I apologize. I'm working with a data file that I did not acquire myself, so there are probably some settings that were not as I thought. But when you are doing it on site with your own setup that is correctly configured for a specific application, it will be very fluid. You will go through all the steps and you will know if the probe is valid or not. As I mentioned, it can be used for to verify a calibration, but also just a functionality check. So in the case of a functionality check, your tolerances will probably be wider than if you want to check at a calibration. So I don't know if there are any questions. I'm a little bit off. I'll just go check in the chat if I can see anything. Okay, so I see a couple of questions here. So Magnifi 4.7 works both for Octane, so on a desktop. So yes, it works for Magnifi, but it also works on Ready. So if you are using Magnifi Go on your Ready system, you will have access to the same tool also. Another question in the chat is regarding, okay, so yes, I mentioned only the spine probe and the iFlex in my example, but it's actually working for all our ECA probe for surface inspection, except for the shark probes. So this might be coming up later, but it's a little bit different processing, so it's not available for the shark probes, but all our other ECA probes in our surface standard lines will be compatible with those tools, as well as the custom probes that we are designing for you. I'm waiting to see. As I mentioned, there's a small delay, so just checking in to see if there are other questions. Okay, one other question. Are the signal rotation and calibration parameters saved in the setup? So yes, when you configure, for example, that you create a setup for a specific application, example, inspection of turbine blades, you know you're doing that inspection 100 times a year and you want to use the same setup every time. If you know that you are calibrating at 5 volts plus or minus 0.25, yes, when you enter those value in the edit settings menu, when you save your setup and your data file, it will be saved with the data information. At the bottom of the video, I think I'll make sure that it's there, but there should be some link to our website or other YouTube videos explaining in more details all the steps of those 2 new features. So you can look at the bottom of the video right now to get more information. I hope you enjoyed. Apology for the small issue at the end. If there is anything, you have my email address at the bottom here of this slide. So if there is anything, you can contact our support team or you can contact me directly. So I hope you enjoyed. And if you have any questions, don't hesitate to contact us. Have a